Hello. So, welcome to the lecture 31, Transient Stability Analysis. That is, we're discussing direct method, and along with that, we'll discuss the voltage stability. So, already we discussed these things when the energy function will be greater than this VPE, that is the potential energy. At that time, the system will be unstable. So how the VP will be evaluated? The VP will be evaluated at this delta equal to delta U cap, that is the unstable equilibrium point. This is one of the unstable equilibrium point. So similarly, we can have here, we can calculate VP delta U cap, and finally we'll get this expression, that is minus PM uh, that multiplied by minus pi minus 2 delta s plus 2p max cos delta s. Now the points delta u and delta u cap, this delta u and delta u cap both will constitute the zero dimensional p base for single meson system, single meson infinite bus system. So it is interesting to relate the potential well concept to the stability of equilibrium points for small disturbances as well. So this method can be used or extended to analyze the small disturbance analysis or small signal analysis. So how we can do this? So this equation already we know, this m of delta square or d square, double derivative of the delta, d square delta by dt square equal to minus of dvpe delta d delta. Already we know this, and we can expand the right hand side of this equation in Taylor series about an equilibrium point delta star, where delta is equal to delta star plus delta delta, and retain the retain only the linear terms. So let us have the derivative. Let us have the Taylor series expansion, that I can write m of d square delta delta by dt square equal to minus d square vp delta by d delta delta square. It is evaluated at delta star and multiplied with delta delta term. So after only we are considering the linear terms here. So then the final expression will become m of d square delta delta by dt square plus double partial derivative of potential energy evaluated at delta star and delta delta equal to 0. So from this equation we can see that the if this double partial derivative of the potential energy evaluated at this equilibrium point is less than 0, then your system is unstable. That means your equilibrium is unstable. And if this double partial derivative of the potential energy evaluated at the equilibrium point is greater than 0, then I can say that this is stable equilibrium point. Then it is an oscillatory system. Obviously it will be an oscillatory system because it will give the uh, conjugate imaginary eigenvalue, conjugate of imaginary, and the oscillations around delta star are bounded. Since there is always some positive damping, we may call it the stable system or stable equilibrium point. So let us now relate the equal area criterion and the energy function. How we can relate this? Let us see. So already we have studied in our undergraduate courses also how the equal area criterion can be. So this here we have shown three curves. So the first curve you can see here, This is your pre-fault characteristic, that is electrical power output. And this is during fault condition, this is during post fault condition. Now if we'll see here, before the fault, under pre-fault condition, this is your equilibrium point. So this is delta naught, and this is the initial operating point, you can say. And as soon as the fault occurred, the operating point moves here, and then it goes back, and here the fault is cleared at delta CL. And then after the fault is cleared, it achieved the post fault characteristic. Okay, so now we can see here there is three curves. So now how we'll relate? So we know by the equal area criterion the system is stable if A1 is less than A2. So this A1, when it is less than A2, your system becomes stable, because if A1 is equal to A2, if A1 is equal to A2, this gives us the critical stability point. That is the critical stability point. That means under this condition we find the critical clearing time. Okay, TCR and delta CR. So so when A1 is less than A2, that means your system is stable. Okay, so let the faulted and post-fault equations we can write this way, that the post-fault equation, or you can say this is the under faulted condition. Under faulted condition, I can write m of d square delta by dt square equal to Pm minus Pef sine delta, and during post-fault condition, m d square delta by dt square equal to Pm minus P max sine delta. So this Pf is during fault, and this P max after fault. They both are different. Their magnitude is different. So here Pf is E1 E2 by Xf, and P max is E1 E2 by X. So the area A1 can be given by this expression. If we'll integrate this area, integrate from delta naught to delta CL, the area between area between PM and PEF, we can find A1. So I can write integration delta naught delta CL with respect to d delta of Pm minus Pf sine delta. So that is equal to nothing but delta integration from delta O to delta CL. So instead of P minus Pf sine delta, I can write m of d omega dt, d omega by dt, d delta. So instead of d delta, I can substitute this omega dt, and dt dt will get cancelled, so it will remain m omega d omega. So now the integration can be from 0 to omega CL, so it will give half of m omega CL. Why it is 0 to CL? Because at delta naught your relative speed is 0, that is omega is 0 at delta naught. So at delta naught omega is equal to 0. So therefore I can write, and at delta CL omega is equal to omega CL. So therefore I can write integration 0 to omega CL, m of omega d omega, and half of m omega CL square is your A1. So hence A1 is the kinetic energy injected into the system due to fault. Area A2 can be given by, we can see here area A2, if we'll calculate, it can be from delta CL to delta U, as we can see from here. Area A2 is covered between the curve, uh, post-fault curve and PM. So I can write the integration of P F sine delta minus PM, and it will be from delta CL to delta U. So I can write here delta CL delta U integration. that is P max sine delta. This is the post-fault electrical power output minus PM mechanical power, and it is integrated with respect to d delta. So after integration, after substituting the values, we'll get P max minus P max cos delta U minus cos delta CL minus Pm delta U minus delta CL. So this is nothing but, I can write this as summation of the potential energy evaluated at delta U minus potential energy evaluated at delta CL. Already we know the potential energy expressions. So just by substituting delta U and delta CL and subtracting, we'll get this expression, final expression. So therefore, this is your A2. Now this is the potential energy curve already we discussed in the last class. So at delta S, the energy is 0, energy function is 0, the value of energy function is 0, and it gradually increases as soon as the fault is cleared. The system becomes conservative, the energy is conserved, and energy remains constant after delta CL. So if we add area A3 to both sides of the stability criterion, that is A1 less than A2, this is your stability criterion. Now the result will be A1 plus A3 is less than A2 plus A3, just by adding A3 both the side. So now evaluating A3, if I'll evaluate A3, A3 can be evaluated from delta S to delta CL, that is P max sine delta minus PM integrated with respect to d delta. It is from the equal area criterion curve, and that will give us minus Pm delta CL minus delta S minus P max cos delta CL cos delta S. So this is nothing but VPCL. So this is nothing but your potential energy evaluated at CL. So delta S is your stable equilibrium point. Now if we'll add A1 and A3, so A1 plus A3, if we'll add, this is your A1 half of omega CL square, and this is your A3. If we'll add this both, this is the energy function at delta CL, that is delta CL and omega CL, that is V of delta CL omega CL. So this is the energy function at the clearing point, fault clearing point. So that is nothing but equal to E, energy. And if we'll evaluate now A2 plus A3, that is equal to VP delta U, right? If we'll now add this to A2 plus A3, then obviously delta PCL will cancel out, only delta P VP delta U will remain. So this is nothing but minus PM into pi minus 2 delta S plus 2P max cos delta S. That is nothing but VCR. That is the critical energy of the system. So that's the equal area criterion, that is A1 less than A2. This is the equal area criterion, and which is equivalent to A1 plus A3 less than A2 plus A3, which in turn is equivalent to nothing but E equal to VCL, V delta CL omega CL. This is the energy evaluated at the fault clearing point, less than the critical energy V shear, that is equal to VP delta U. So from the equal area criterion also we concluded that, so your stability will be maintained if your E is less than VCR, that is E is your energy function evaluated at the fault clearing point. This is constant. If it remains less than the critical energy of the system VCR, that is nothing but the potential energy at the unstable equilibrium point. So then your system is stable. So let us consider one example. So consider a single machine infinite bus system. So this is the under faulted system. The equation is, let us say this, that is 0.2 d square delta dt square, that is equal to 1 minus sine delta, minus 0.02 d delta dt, and the post-fault system is given zero point 0.2 d square delta upon dt square, that is equal to 1 minus 2 sine delta minus 0.02 d delta by dt. So this is post-fault system. Now the question is, we have to state analytically the equal-area criterion, compute TCR using the results of part 1. So we have to find out analytically based on the equal-area criterion. So note that the energy function is for a conservative system, right? So while the faulted system is not conservative, so obviously, so the energy function is given by this equation that is V delta omega is equal to half of 0.2 omega square minus delta minus 5 by 6. Just by substituting the clearing point, we'll get the energy function at the stable equilibrium point. So this is your energy function, 0.1 omega square minus delta minus 2 cos delta plus 2.256. Now, if I'll evaluate the critical energy of the system, that is V delta U0, I can write minus Pm pi minus 2 delta S plus 2 P max cos delta S. Just by substituting the values delta S, I'll get 1.374 as the critical energy. So hence the equal area criterion states that your V delta CL omega CL, that is the energy at the fault clearing point, should be less than 1.374. So here delta CL omega CL are calculated from the fault and trajectory. From this trajectory, we can calculate the delta CL and omega CL. Now this faulted system will be integrated to find. So this faulted system will be integrated to find the time domain solution of delta T and omega T. So the critical clearing time can be computed from the trajectory of delta T and omega T by considering the values of delta CL and omega CL, such that your V of delta CL and omega CL should be equal to 1.374. When this is equal to this, so your delta CL will be equal to your delta CR, that is the critical clearing angle, and from this I can find the TCR from delta TCR from the delta delta trajectory. So easily I can find it. So now let us consider, up to this point we discussed the single machine infinite bus system. So let us consider the multi-machine potential energy boundary surface. How can be implemented in the multi-machine system? So in case of multi-machine system, the PEBS is quite complex in the rotor angle space. A number of unstable equilibrium points surround the stable equilibrium point of the post-fault system. So the potential energy boundary surface therefore constitutes a multi-dimensional surface passing through the UEPs. So it's really difficult to analyze here with pen and paper this multi-machine PEVs. Already we discussed the generalized formulation. We can directly use that and find the energy function and the critical energy, and we can evaluate the energy function at the clearing point, and then we can find the critical clearing time. So methods of improving transient stability. So up to this point we saw transient stability analysis by numerical integration method, then by direct method we saw. Then now we'll see how we can improve the transient stability of the system. First point is high speed fault clearing. This is very important. This plays in fact very important role in improving the stability. So the amount of kinetic energy that is gained during a fault. So the kinetic energy generally gained during the fault and it is directly proportional to the fall duration. So as the fall duration will increase, the kinetic energy gained by the system will increase. Hence, the faster the clearing, better the stability. So as soon as the clearing is faster, if will as soon as the fault is cleared, the kinetic energy increase in the system will stop, and therefore the system will be the stability of the system will be improved. So therefore, fast-acting circuit breakers can be used for clearing the fault within 2 cycles through better communication and fast-acting relays. And second point is your uh, reduction of transmission system reactance. It is the stability improves with reduction in the system reactance as it enhances the synchronizing torque. This can be done by series compensation. So we know the synchronizing torque coefficient is a function of reactance, the series reactance. As the series reactance will be decreased, the synchronizing torque will improve or readily enhanced. Hence, by giving the series compensation in the transmission line, series compensation means adding the series capacitances in series with the line, we can reduce the reactance, net reactance. So therefore, the synchronizing torque will increase. Also, the transformers with lower leakage reactance can be used in order to improve the transient stability by reducing the transmission system reactance. So regulated sound compensation. Sound compensators like SVC, STATCOM can be used for improving the voltage profile, thereby synchronizing the power among interconnected generators. So SVC and STATCOM, they are the sound compensators. They are used to maintain the voltage. So this helps us in fact synchronizing the system. So then this is third one. This fourth one is independent pole operation of the circuit breakers. So instead of switching out all the 3 phases for every fault, only the faulted phase may be switched out. So this will significantly improve the stability of the system. Then fifth one is your dynamic braking. So during a fault, the input mechanical power to the generator is greater than output electrical power, leading to the acceleration. So when the fault occurs, the mechanical power becomes greater than the electrical power, and therefore the rotor accelerates. Instead the excess power available due to this mismatch between input and output powers can be absorbed by the resistors, which can be connected to the generator terminals during the fault. So these resistors are called braking resistors, as they will decrease the acceleration of the rotor by absorbing the excess power. The disadvantage of this method is that the power is lost in the form of heat, and therefore the dissipation mechanism should be developed in order to dissipate the heat produced in these braking resistors. And sixth one is single pole switching. Again, instead of tripping all 3 phases and then reclosing all 3 simultaneously, each phase can be tripped and reclosed with 0.5 to 1.5 second, so that other 2 phases are still working in case of single line to ground fault, as they are the most common faults. Then fast valve operation. So it is a technique applicable to the thermal units to assist in maintaining the power system stability. We know the governor mechanism. So if the governor mechanism is faster, then it actually it helps in balancing the power mismatch very quickly. So it involves rapid closing and opening of the steam valves in a prescribed manner to reduce the generator accelerating or decelerating power following the reception of a severe transmission system fault. Then the tripping of the generator, selective tripping of generating unit for severe transmission system contingency has been used as method of improving the system stability for many years. And using supplementary damping controllers like power system stabilizer or supplementary feedback controllers to the fax devices can improve the small signal stability. It helps in damping the oscillation. So using HVDC links, HVDC links can also improve the small signal stability by modulating the power in the DC link. The small signal oscillations can be damped by using this method. So this is all about your transient stability. And now we'll talk about the voltage stability. So voltage stability is your final topic of your course. So another stability issue which is important other than angle stability is voltage stability. And voltage stability can be defined as the ability of the system to retain system voltages within acceptable limits when subjected to disturbance. This is the definition of the voltage stability. If the disturbance is large, then it is called as the large disturbance voltage stability. And if the disturbance is small, it is called as the small signal voltage stability. Similar to the angle stability, small signal and large signal. So voltage stability can be local phenomena where only a particular bus, so it's very local phenomena. So rather than the global phenomena, or buses in a particular region have voltage stability issue, and this may not affect the entire system. So voltage stability can also be global phenomena where many of the system buses experience voltage stability. So this is called the voltage collapse. Sometimes it happens and it causes the blackout, which can also trigger the angle stability problem along with this, and hence can affect the entire system. Some of the voltage stability problems can start as a local problem and escalate to global stability problem. Voltage stability of a system can be analyzed either by static analysis or dynamic analysis. So both can be used. We'll talk about these two. In static analysis, the system is assumed to be in steady state, and hence instead of taking the DAE, differential algebraic equations of the system, only the algebraic equations are considered for the static analysis. So this type of analysis is suitable for small disturbances in the system. Whereas for large disturbances, for large disturbances, the for large disturbances, the DAE are solved, differential algebraic equations are solved, and the system response over a certain period of time is observed. It is important that for voltage stability, the load should be properly modeled, as each type of load will affect the system voltage stability in different way. So we'll see this how different types of load will affect the voltage stability in different way. Generally, we'll do the analysis considering the constant power load model. Similarly, the tap changing transformers, shunt or series reactive power compensators, generator reactive power limits, line charging capacitance should be included in the system representation because these facts, these tap changes, series and reactive power compensators, reactive power limits, charging capacitance, they all affect the voltage. So therefore, this model, when we're modeling this for voltage stability analysis, all these models should be considered very accurately to get an accurate picture of the voltage stability. So let us consider the basic concept here, basic concept of the voltage stability. So to understand the concept of the voltage stability, let there be a two bus system with one end being sending end and other being the receiving end, as we can see here in the figure. So Vs is the sending end voltage and Vr is the receiving end voltage, and Zt is the reactance of the transmission line, and or you can say impedance of the transmission line, and Zl is the impedance of the load. And the magnitude of current in the transmission line that can be given as taking the sending end voltage as reference. If we'll take the sending end voltage as reference, then I can write the current expression or the equation of the current as Vs0 by Zt plus Zl, the magnitude of this. So I'll find that is Vs by Zt square Zl square plus 2 Zt Zl cos of theta t minus phi l square root. So theta t is the angle of the Zt, that is ZT impedance, and phi L is the angle of ZL. So the receiving end voltage magnitude is, then we can define this receiving end voltage as Vs ZL, current into ZL, magnitude of the load impedance. So the real and reactive power consumed by the load can be given as, the PL I can write I square R RL. I square is nothing but this current magnitude square into R is ZL cos phi L. So I square R I can write in this format. And then QL is I square XL, that is VA square ZL sin phi L. Okay. So let the transmission line impedance be taken as ZT equal to 0.25 per unit, neglecting resistance as usually. The reactance to resistance ratio, because the reactance to resistance ratio in a transmission line is quite high. So here we are neglecting the effect of resistance and considering ZT as 0.25 per unit. This is the reactance only. So let the sending end voltage be 1 per unit. The real and reactive power of the load can be increased by decreasing the load impedance. If we'll decrease the load impedance, that gives the effective load to be increased. So, and maintaining the a constant power factor, say at 0.8. So maintaining the constant power factor. So the receiving end voltage is plotted in below figure with varying real power consumed by the load with the parameters mentioned above. So this curve is called as PV curve. So you can see here this, if we'll considering this by increasing the real power load, that means we're decreasing the load impedance. And if we'll plot this with respect to receiving end voltage, we'll get this kind of curve. So this curve is known as PV curve. Okay. So this is your knee point the where the power actually in fact decreases as we increase further the power load impedance further we decrease the load impedance further. So it can be observed from the PV curve that as the load increases from no load condition, the receiving end voltage starts dropping from initial no load voltage of 1 per unit. The increase in the current I due to decrease in the load impedance ZL is more here than the drop in the receiving end voltage magnitude, and hence the real power consumed by the load will increase. So up to this point, up to this knee point, if you'll see, the though the voltage is decreasing but the real power is increasing, it is because the decrease in the load impedance causes the increase in the load current more as compared to the drop in the voltage VR. So the maximum real power 1 per unit will be delivered to the load when ZL equal to ZT. Once operating point reaches the maximum power point or critical point or knee point of the curve, any further decrease in the load impedance to increase in the load will result in further drop in the receiving end voltage, and simultaneously the real power consumed by the load will also decrease. So it means after the knee point, that is the maximum power point or critical point or knee point, after the knee point the decrease in the load voltage will be more as compared to the increase in the load current because of the decrease of the load impedance or increase in the real power of the increase in the load and the system. So this is because after the knee point the drop in the voltage is more than the increase in the line current, leading to a decrease in the real power consumed by the load. So this is all about your voltage stability little bit. So next class we'll discuss more of this voltage stability in detail. So next class maybe we'll finish this course. So thank you very much.